Welcome to Advanced Group Theory. Today we are going to explore a fascinating and powerful topic called group actions. If you have ever felt that abstract algebra is just a floating list of rules with no real purpose, this lesson will change that completely by giving those rules a physical job to do. Before we look at the math, let us understand why this concept matters. Imagine you are holding a video game controller. The buttons you press form a group of commands like jump or move left. The character on your screen belongs to a set of positions. When you press a button, the character moves. The abstract command is the group element, and the movement is the action. A group action is simply a set of instructions telling objects in a set how to move around. Now that we have our video game analogy in mind, let us look at the formal mathematical map. This formula shows where a group action comes from conceptually. The capital G represents a group of commands and the capital A represents a set of objects. The cross symbol means we take one specific command from G and pair it with one specific object from A. The arrow shows that applying this command produces a result that lives back inside the set A. In plain English, take a command, apply it to an object, and you get a new object state back. This mapping formula we just saw leads us to an important question. What makes an action mathematically valid? To be a true group action, the rule must obey two strict laws. The first is the identity rule. Every group has a do-nothing command, and applying it must leave the object exactly where it is. The second is the compatibility rule. If you apply two commands one after the other, the final position must be exactly the same as if you had combined the two commands first into a shortcut and applied that single shortcut move. Let us translate that first law into a mathematical formula. This equation represents the identity rule. The letter E stands for the identity element of the group, which is the command to do absolutely nothing. The dot symbol represents the action taking place, meaning acting upon. The letter A is a specific object from our set. The formula simply states that when the do-nothing command acts upon the object A, the result is exactly the same object A. If this does not happen, the action is invalid. Now let us look at the formula for the second required law, the compatibility rule. Here, G1 and G2 are two different commands from our group. On the left side, we first let G2 act on the object A and then let G1 act on the new result. On the right side, we combine the two commands inside the group first to create a single new command and let that act on the original object. The formula guarantees both paths lead to the exact same final object, no matter which commands you choose. Before we move on to more complex ideas, let us see this with a concrete example to build your confidence. We will use a permutation group, which is a specific way of shuffling items. We are given the group S3, representing all possible ways to shuffle 3 items, and our set A contains the actual numbers 1, 2, and 3. We are asked to apply a specific swap command, replacing 1 with 2 to the number 1. We set up our equation by substituting our specific group element and set element into the action map. Continuing with our calculation, we execute the swap command. The command tells us to replace 1 with 2, so the result is simply 2. Next, we quickly verify the identity rule. The identity element E tells us to leave all numbers exactly where they are. Applying E to the number 1 returns the number 1. This physically shows how an abstract shuffling group acts on a concrete set of numbers, and our final answer confirms the rule holds perfectly. Now that we have used a basic permutation, let us look at a real-world geometry example to test the compatibility rule. We are given a square with 4 corners labeled 1 through 4 in clockwise order. Our group is the set of rotations, and we choose a 90-degree clockwise rotation called R. We are asked to find the result of applying R twice to corner 1 and verify that it equals applying the combined double rotation R squared to corner 1. Let us work through the left side of our equation, step by step. We start inside the parentheses. Applying a single 90-degree clockwise rotation to corner 1 physically moves it into the spot previously held by corner 2. So, R acting on 1 equals 2. We substitute this result back into our expression. Now we apply the second rotation to this new position. Rotating corner 2 by 90 degrees moves it to position 3. We have found that sequential rotations move the corner to position 3. Now we must check the right side of the compatibility rule. The element R squared represents combining the two 90-degree rotations into a single 180-degree rotation command before we even touch the square. Applying this combined rotation to corner 1 moves it directly across the diagonal to position 3. Both methods yield the exact same physical location, proving the compatibility rule works perfectly. This diagram visually confirms the math we just proved. Look at the square on the screen. You can see the 4 corners labeled 1 through 4 in clockwise order. The large arrow in the center represents our group element R, the 90-degree rotation. The dashed arrows on the outside trace the physical path of corner 1. It first moves to position 2 and then to position 3. This visual tracking is exactly what the mathematical dot notation was doing behind the scenes. Now that we have seen how the math and geometry work, why does all of this matter? Group actions are the ultimate bridge between abstract algebra and the real world. Without them, groups are just isolated tables of symbols. With them, we can solve incredibly complex counting problems, like figuring out how many unique necklaces you can manufacture using different colored beads. In chemistry and physics, scientists use group actions to study the symmetry of molecules, predicting how they will vibrate, absorb light, and react. Let us wrap up what we have learned today. First, a group action is simply a way for an abstract group to manipulate a concrete set of objects. Second, any valid action must obey the identity rule, where the do-nothing command leaves objects exactly as they are. Third, it must obey the compatibility rule, ensuring that sequential moves always match combined shortcut moves. By mastering these concepts, you have unlocked a powerful tool to analyze symmetries and permutations in the physical world. Great job!